with the first inference statistics topic, which is the distribution of sampling statistics. So let's look into these words, the distribution of sampling statistics. So if you remember some basic things about population and sample, you may recall the word statistic and parameter. So when I say sampling statistics, it's all of these informations, all of these data, all of these summarizations, that we can take from our sample. If you recall, we could compute the mean, we could compute the variance, we can compute many things that would tell us something about the sample. So in order for us to understand how we can use the information from the sample for the population, there are some important concepts that you need to know. First, we have our random variables, our trustworthy random variables. By now, you probably already know what these are. We've gone over these so many times, in total around 5 weeks on random variables. But the most important part that I would like for you to focus on is that each occurrence of any random variable, regardless of what is it discrete or is it continuous, is it exponential or is it uniform, it doesn't matter. Whatever random variable you have, it will have a certain probability distribution. We don't know its shape. We don't know, we might not know its shape. We might not know how wide it is or how high it is, where it is centered, and et cetera, et cetera. We don't know that, but we know that it will have a probability distribution. And this probability distribution, as we have learned in random variables, it will give us the probability that our random variable has a certain value. What's the probability our random variable has a value of 2? What's the probability our random variable has a value of 0, and so forth. And this is the main concept. So now we are going to remember about the parameter and statistics. As I already mentioned previously, from our title, we already had the word statistics. So remember, when we are studying anything, like we're studying the population of UI students, for example, there are parameters that you would like to know. For example, I want to know the mean height of UI students. I would like to know the mean GPA of UI students. I would like to know the mean typing speed of UI students, for example. However, it is impossible. It's not feasible for us to actually take the data of the entire population. So we are forced to take statistics from the sample. So I could study maybe 100 students of 100 UI students only, and that's doable. I can compute the mean or the average GPA of these 100 students. It's doable. So keep in mind that when I compute that mean of the 100 students, I'm not taking the parameter. I cannot compute, like, for example, I know that from my 100 students here, I obtained a mean GPA of 3.5. So this 3.5 here does not yet tell me anything about the population. Not yet. I only know this is valid for this particular sample. Imagine if I took a different sample, maybe from a different faculty, maybe from a different cohort. This is no longer valid. I would get some other mean. I would get some other mean. Maybe it's 2.8. Maybe I would get another mean. I would get 3.7, for example. So how can we do that then? If every sample I take is going to give me a different result, how is it that I can infer something about my population from that statistics? It seemed, from this previous explanation, it seemed rather unreliable. It would change, the mean would change every single time. So in order for us to be able to do so, we do need to implement some assumptions so that we can do this inference. Okay, so these are the assumptions that are needed for us to make these types of inferences. So first, we have to assume that We don't know them yet. We don't know the mu and the sigma of the population. I don't know it. However, I do know that there is some underlying probability distribution of it. It may be normal, it may be something entirely different. It could be any graph at all. But I know that there is some probability distribution of these parameters. Next, so every time I take a value of that population, like for example, so if I'm talking about the population's parameters, so there is a probability distribution of the population's mean. So the mean of the population would follow some sort of probability distribution. I don't know the shape yet. I'm just drawing a normal one here out of habit. I don't know what it is yet. And then next, every time I take a member of that population, in other words, I take a mean from a sample, I could say that that is an independent random variable which will follow this same distribution. Say F, I'm just giving a random number. I know that, oh, I'm taking one average here. Oh, this will follow F. I have another one here. Oh, it will follow F. Because I'm assuming that every single sample I take and I compute the mean of, it will be a member of this type of distribution. It will follow that same one. Thus, when I take randomly sampled data, if I take 100 here, 100 there, and so forth, then I can also assume that that sample data will also follow that same distribution. F that I don't know what it is yet. I just know that it will follow that distribution. Okay, so based on these assumptions, then, if I say that I have x1, x2, xn of independent random variables, and I know that they have a common distribution F, I don't know what it is. It could be normal, it could be exponential, I don't know, but it has a common distribution n. Then I can say that they constitute a sample of size n from the distribution F. So I know that each and every one of these data samples that I took are a random independent random variable with distribution n. And now from these data samples that are observable to me, then I now want to infer the parameter of the population itself. So we have two inference problems that could be done. First is the parametric inference, in which I have a certain amount of unknown parameters, and I also have some assumptions. And I also, obviously, I need to restrict my problem somehow so that it is solvable. And the next one is non-parametric inference, in which nothing is assumed about F, and I just do a genuine estimation. Obviously, the first one is a lot easier than the second one, and that is what is going to be covered in this course. If you're interested about the non-parametric inference, then I don't believe that there is a sufficient statistics course that is offered in Fasilcom. However, further statistics will cover this type of inference. Okay, so with using the parametric inference, we need to take an inference about a population distribution F. So that distribution here, so I know that the mean would follow some sort of distribution. I don't know what it is. And I want to be able to estimate this using the statistics I take from the sample. And I would like to take the probability distribution. I want to find, the probability distribution of these sample statistics. I'm not trying to find the exact value yet, but I'm trying to find the probability distribution. So at the end of a parametric inference here, I will not be able to say, oh, the mean GPA of the population is 3.7. I would not yet be able to do that. But I would be able to say that, oh, the mean GPA of the population will follow this distribution. So we go back to these data samples that we had in the previous discussion. So if I were to take some samples many times, maybe 10 times, maybe 12 times, I don't know. Every single time I take a data sample, which are I'm assuming them that they're going to be random, I could compute two things. I can compute the sample mean, I can compute the sample variance. Although I don't know the population mean, I do know the sample mean. And based on the central limit theorem, I will be able to use these two measures in order to estimate the distribution of the population mean. So in order to do that, I'm going to, the central limit theorem, in order for it to understand, you need to know how to compute the sample mean. So since we have already established that for any sample that you were to take, any X that you were to take from randomly from a population, we know that each of these X1, X2, X3, and so forth, these are random variables. And if you remember, when we were studying the combinations of random variables, then we also know that the combination, the linear combination, of a random variable would equal to a random variable as well. And in this case, you can see here that when I do a sample mean, when I take the sample mean, I'm summing up all of these random variables and I'm multiplying it by 1 per n. Remember that dividing by n is just multiplying with 1 per n. And 1 per n is a constant, so it is a linear combination. And thus, X bar, or the sample mean, will also be a random variable, which then again would follow the same logic as previously, that the random variable X bar will also be following the same distribution that is underlying, that is the underlying distribution of the population mean. So if I were to plot the probability of my X bar, as was also shown in the previous video, then I would end up with something that looks like this. So my sample mean, if I were to sample it, as you saw before, we could sample it from any distribution, any underlying distribution, and it would end up looking something like this. It would end up looking like a normal distribution. So since I know that the X bar is centered about the population mean, mu, it's centered around the same place. But based on the sampling that I do, it might not be perfectly normal. So it would be centered at the correct spot, but it could be a little bit wider, it could be a little higher, and so forth. However, thanks to the handy central limit theorem, apologies. So based on thanks to the central limit theorem that we've already established, based on that, then we know that if I can assume that these n data samples is an independent random variable with some distribution, with some expectation and variance, which I don't know yet, then if I have a large enough n, I could approximate the sum of all of these data points to be a normal distribution. Note that them individually, it's still a random distribution of f, which I don't know yet. But if I were to sum them all up with a sufficient amount of data points, then I can say that they would follow the normal distribution. And as you can see here, since it's a normal distribution, we know for a fact that the mean and variance I can take the multiplication of n and mu of the individual ones and the multiplication of n and variance of the individual ones as the parameters of this approximated normal distribution. And since it is a normal distribution, I know it's normal, I can also try to convert it into a standard normal random variable. Remember that when we had any type of normal random variable, our immediate objective would be to try to convert it to a standard normal random variable, because that way I know for sure it's centered at 0 and it has a standard, a variance and standard deviation of 1. And how did I get this? as you know, I'm just doing x minus mean divided by standard deviation. So from here, I know that this is the mean. I know that this is the variance. So if I wanted the standard deviation, then it would be that, right? In other words, sigma square root of n. And that is why this is used in the bottom and this is used on top. So by doing that, I can then assume that this is a standard normal variable, and thus I can use it. I can use the standard normal table and its CDF to compute its probability. So I can use the pi here to compute its probability. So let's look at an example. So we know that this insurance company has 25,000 automobile policyholders. So here we know that our N is 25,000. I know that there are 25,000 automobile policyholders. And then I know that a yearly claim of a policyholder is a random variable with mean 320 and standard deviation of 550. So what do we know here? We know this, we know the mean, and we know the standard deviation. And now I want to compute the probability that the total yearly claim exceeds 8.3 million. Okay, so I'm going to give you some pause. So the first step that we need to do that sometimes I'm also guilty of forgetting, don't forget, we first need to declare all of the information that we have. So let's say that, X is yearly claim, is the yearly claim of this insurance, right? And since I know that I have 25,000, I have XI, which is the yearly claim of person I. So we know that we have 25,000. And this will give us the chance to declare each and every person's yearly claim as a random variable, as well as the total as well. So, sorry, my slide is not moving. Okay. So if I know this, and I know that N is 25,000, and I know that this is my mean and this is my standard deviation, then I can remember my central theorem, my central limit theorem, the sum of all of these observations, and I know that the sum will follow that. I know that the sum would follow that distribution. So I'm just going to copy that real quick. Copy that to our slide. Is it in? Yeah, I already copied it. So I know that this would follow a normal distribution with N times mu. So 25,000 times 320 and 25,000 times my variance, not standard deviation. So this would be something like that. Okay, so that is just an approximate. So I already computed this, I think. Give me a sec. Where is it? I already computed it somewhere. Oh, there you go. So here I already know that this would follow something like that. There we go. So I had already computed the multiplication, and I know that the sum would follow this normal distribution. And using this one, because now I know that it's a normal one. Previously I didn't know, but now I know it's normal. So I can now compute that the probability that the total yearly claim exceeds larger than 8.3 is then as follows. Note that my first step here is to convert it to a standard normal variable by minus mu divided by standard dev, and also here, and then I can, this is obviously an approximation because we're using a lot of commas here, and I can use the table to compute the, I can use the standard normal table to compute the probabilities. So here you know that there's two ways to do that, and I could use the other way around, the symmetrical property of the normal distribution, and I can obtain, this is the probability that the total yearly claim would be somewhere larger than 8.3 million. So note here that when I had only one singular data points, x1, x2, x3, I could not yet use that to infer something about the population. However, when I started to sum them up, I could. So note that this is my population. I took a sample. From this sample, I have different observations, x1, x2, and so forth. I can't do anything with this yet. But if I sum them up, I can. And if I take the mean, I can. So I'm trying to convert these in observable data points into something that would follow a normal distribution. And up until now, this example only proves this top part. So it has proven that if I sum up enough, data points, I can get an approximated normal distribution. And apparently, if I were to take the mean as well, as you know that previously the mean is just the sum up divided by n, right? So since I know that the summing up is already a normal distribution, if I were to divide it by n, or in other words, multiply it with 1 per n, it's just another linear combination. And thus I know that this one here, the mean, the sample mean, will also follow a normal distribution using these parameters. So I divide it by n, right? So if previously the sum of x would follow n mu and standard deviation, variance, then if I were to divide it by n, then I would obtain this here. So the sample mean of x will also follow the same, this distribution here. And from that, we can then infer a couple of things: the expectation of the sample, the expectation of the sample mean, the variance of the sample mean, and so forth. So up until here, we had some different things that we are already starting to be able to infer. So we have some samples, we have some distributions, and now what we want to do is we want to try to use it to estimate something about my entire population, because as you know, it's not really useful for me to know something about a certain sample, because that's not it. But what we want is inferring something about the entire population. You may recall that in the previous video, this is also covered that. So how large of a sample do I need to take in order for me to be able to use the central limit theorem? So just like the video said, this book, the book that we are using as the reference book of statistics, is also using the same rule of thumb. It says that I can say that the sum and the average is approximately a normal distribution if I have enough samples. So if I have 30 samples. But this is arguably only a rule. So in most cases, the normal approximation is valid for much smaller sample sizes. And as the guy mentioned in the video as well, this is only a rule. So in the context of this statistics course, you do not need to put up the assumption of how many samples you have. You are allowed to directly implement the central limit theorem in any type of inference. You can assume that this normal approximation is always valid in the context of this class. As well, in the previous video, we were assuming that the sample taken is very small compared to the population. So if I had a population of 1,000 people, maybe my sample is only 10. If I had a population of 200 million people, population of Indonesia, for example, I'm only taking 100 people. That is why we use an approximation that we try to make it into a normal one. But what if my population is rather small? So if I have a finite population, which is the case in many like smaller statistical experiments. So if I only have 100 people in my entire population, arguably I could just I could just take data from all 100. It's still feasible. But you could also formulate it differently. So if I have n elements, and I have the assumption that P is a proportion that has a certain characteristic. Maybe P has a GPA larger than 3, like 0.6 is the proportion. So 0.6 people, 0.6 parts of my population has a GPA larger than 3, for example. But if I know that P parts of the population has this property, then I know that 1 minus P does not. And then I can take any random sample and it's equally likely to be selected as the sample. And for every single sample that I ask, hey, is your GPA larger than 3? There are two possible outcomes. Either yes, the GPA is higher than 3, or in other words, it fulfills that correct characteristic, or no, 0. And doesn't this remind you of something? It would remind you, hopefully, of the Bernoulli random variable, in which we do experiments that have only 2 possible outcomes, either yes or either no. And if I do that, then one person would be a Bernoulli random variable, and the collection of n people or n Bernoulli random variables would be the binomial random variables. And thus, if I wanted to implement the central limit theorem for binomial random variables, then there are some different approximations that we can use. So instead of previously, we had sum of x minus mu, and the bottom one is the standard deviation. We can use NP instead as our mu, and that bottom denominator as our standard deviation. Then we can approximate the standard normal random variable.